Okay, we took a look at the different experiments that helped scientists find the parts to an atom and their location. We're going to continue with the evolution of the atomic theory and how we count atoms. Remember that Democritus looked at matter and said if you took a segment of matter and cut it in half and cut it in half and cut it in half, and you continued, you'd eventually get down to one single atom. Okay, Dalton's atomic theory. Elements are made of tiny particles called atoms. All atoms of given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements combine in simple whole number ratios for compounds to form. In chemical reactions, atoms are combined, separated, or rearranged. Atoms cannot be created or destroyed in a chemical reaction. They are simply rearranged, which is the law of conservation of mass. The amount that we start with is the same as what we would end with. In looking at the law of definite proportions, this comes from Dalton's atomic theory. A given compound is always composed of the same combination of atoms. So in other words, the definite proportion, meaning the definite ratio between elements, isn't going to be set for that compound. In our examples, let me get my pen. In our example, the carbon monoxide's formula is CO. It has a ratio of 1 atom of carbon to 1 atom of oxygen. That is the set definite proportion for carbon monoxide. Water, you know, is H2O. 2 atoms of hydrogen to 1 atom of oxygen. It's a 2-to-1 ratio for hydrogen to oxygen. That is the definite proportion for water. The law of multiple proportions, when 2 elements combine to form more than one compound. So our first example is looking at carbon and oxygen. We know that in a 1-to-1 ratio, 1 atom of carbon to 1 atom of oxygen, we can make carbon monoxide. We can change that ratio, multiple proportions, 1 atom of carbon to 2 atoms of oxygen gives us carbon dioxide. Same elements, but now I have multiple proportions. I had a 1-to-1 proportion for carbon monoxide and a 1-to-2 proportion for carbon dioxide. Looking at hydrogen and oxygen, we know water is H2O, 2 hydrogens to 1 oxygen, a 2-to-1 ratio. Hydrogen peroxide is H2O2. That's 2 atoms of hydrogen to 2 atoms of oxygen. Multiple proportions, but the same elements. The modern atomic theory, Dalton turned Democritus' idea into a scientific theory that could be tested by experiments. Not all of Dalton's atomic theory was correct. Atoms are able to be divisible into smaller particles, although the law of conservation of mass still holds true for the chemical reaction. And elements can have atoms with different masses. Dalton's atomic theory has not been discarded, it's just been modified. All matter is composed of atoms, and atoms of one element differ in properties from other atoms of other elements remaining unchanged. Looking at the mass number versus the average atomic mass. As we take a look at the mass number first, the mass number is the number of protons plus the number of neutrons added together. That gives us our mass number. It's going to be an integer. It's a specific number for A. A is just a symbol that they used in chemistry to represent a mass number. The mass number does not have units. And there are, when you look at the periodic table, you're not going to see the mass number. You can figure it out by looking at the periodic table, but the periodic table will not contain the mass number. The average atomic mass, this is a weighted average of all the naturally occurring isotopes. Isotopes are the same element, but their neutrons differ. If you were to imagine a box of apples, even though everything in that box is the fruit apple, they're not all the same mass. There's something different about them. And it's kind of what an isotope, their neutrons are different, so it's going to affect their mass. And we'll look at isotopes in more detail. But your average atomic mass, which you would find on the periodic table, it's a weighted average of all the naturally occurring isotopes. Since it's a weighted average, you're going to see a decimal number. It's not a specific mass for a specific isotope. It's a weighted average of all of the naturally occurring isotopes. And the units for average atomic mass are AMU, which stands for atomic mass unit. When we're looking at the mass number, remember the mass number is not on the periodic table, but we can figure it out by looking at the periodic table. The mass number needs to be a whole number. So the average atomic mass is what you would find on the periodic table. Remember, this is from the periodic table. If you looked at a periodic table for the elements that I have listed here and looked at the average atomic mass, these are the values you would find. To get the mass number, we want a whole number. So we have to round the average atomic mass to a whole number. In order to round that to a whole number, we have to look at the tenths place to decide if we round up or not. So for hydrogen, we have a 0 in the tenths place. Less than 5, we drop it. The mass number of hydrogen is 1. Hydrogen, the tenths place is a 9. 5 or greater, we round up. So oxygen would go to 16. Sodium, tenths place is a 9, so sodium's mass number would become 23. Potassium, the tenths place is a 0, less than 5, we drop it, so the mass number for potassium is 39. The average atomic mass, remember the average atomic mass is listed on the periodic table. If you look at the periodic table, it's the weighted average of all of the naturally occurring isotopes, and it has the decimal number. So, these are what's listed on the periodic table. When we use the average atomic mass number, we round it to the hundredths place. So we're going to round to the hundredths place, and in order to round to the hundredths place, we have to look at the digit found in the thousandths place to decide how to do the rounding. Looking again at hydrogen, we go to the thousandths place. That's going to be 3 places past the decimal. So I'm looking at the 7. 5 or greater, I round up. That's where I'm getting 1.01 for the average atomic mass of hydrogen. Iron, if I look at the thousandths place, there's a 5. 5 or greater, we round up, so that 0.84 is going to become 0.85. 55.85 is the average atomic mass for iron. Sodium, looking at the thousandths place, I have a 9. 5 or greater, I round up. So sodium's average atomic mass that we would use is 22.99. And then potassium, looking at the thousandths place, I have an 8. 5 or greater, we round up. So that would be 39.10. Now let's take a look at the subatomic particles. For our class, we are only looking at protons, neutrons, and electrons. Beginning first with the protons. Protons carry a positive charge, so they're abbreviated a P with that subscript or a superscript of a plus, indicating that they carry a positive 1 charge. Protons have a positive 1 charge, and they're located inside the nucleus. The number of protons represents the atomic number. When you look at the periodic table and you see the atomic number, that's going to tell you the number of protons. This is also known as the Z. If you see a question that says, what is the Z for hydrogen? They're asking you for the atomic number. The atomic number, again, is the number of protons. It is also what identifies the element. If you change the atomic number, you change the number of protons. If you change the number of protons, you change the identity. Therefore, you would change the element. The atomic number is going to identify what element you're looking at. Next, we're looking at neutrons, and this is actually abbreviated N with the little null sign. Let me write it a little bigger. I can't write that small. There isn't a charge on the nucleus, or excuse me, there is a charge on the nucleus, but the neutrons are neutral. They are located inside the nucleus. To find the number of neutrons, you would take the mass number minus the atomic number. Remember that A is representing the mass number, Z is representing the atomic number. Mass number, again, if you'll just recall mass, put this over here. Mass was protons plus neutrons added together. So if you took your mass number and subtracted your atomic number, let me write this down here, sorry, a little bit neater. Protons plus neutrons. That's going to give me my mass number. And if I subtract Z, which remember Z is representing the atomic number, and the atomic number is protons, if I take the protons out, you're only left with the neutrons. So mass number minus the atomic number is the number of neutrons. Isotopes of the same element have a different number of neutrons. Remember, isotopes are what's going to cause a little variation in your elements. If you had a box of carbon and they're all carbon atoms, you could have variations in those carbon atoms due to the isotopes. And what makes them different is the different number of neutrons. If you change the number of neutrons but keep the number of protons the same, you still have the same element, but changing the neutrons is going to change the overall mass number. Our last one is the electrons. They're abbreviated E with our superscript of a negative because the electrons carry a -1 charge. The electrons are located outside the nucleus in orbitals. For neutral atoms, the number of protons equals the number of electrons. Neutral atoms, positive particles, equal negative particles. All right, guys, as we take a look at these examples, have your periodic table handy so that you can see where I'm getting these numbers from. All right, starting first with lithium. The mass number for lithium is 7. Remember, your mass number gets rounded to a whole number from the average atomic mass on the periodic table. And then the atomic number for lithium is 3, which it gives us our atomic number. Protons are going to equal the atomic number. These two equal atomic number and protons. So 3, 26, 8, 17 for all of our elements. Again, protons are the atomic number. To find my electrons, protons in a neutral atom, and everything we're looking at right now is neutral. Protons equal electrons, or positives equal negatives. So I have 3 electrons, 26 electrons, 8 electrons, and 17 electrons. These guys would equal because they're neutral. And then to find our neutrons, remember we're going to take mass number minus atomic. That gives us our neutrons. Mass, again, remember, was protons and neutrons added together. Atomic number was protons. We're going to take our protons out. That's going to leave us with our neutrons. So 7 minus 3 for lithium gives me 4 neutrons. 56 minus 26, 30 neutrons. 16 minus 8, 8 neutrons. And the last one, chlorine, 35 for our mass number minus our atomic number of 17 gives me 18 neutrons. Okay, now it's your turn. I have 4 elements here. You need to use your periodic table, do the mass number, atomic number, protons, neutrons, and electrons, and we'll go over them next class.